Hello everybody, we've got a slightly new format for this video, as you can see. Maybe you're familiar with it from Professor Austin's videos in the fall, but let's see how it goes. Today I want to think about a seemingly silly SN2 reaction. So let's imagine that we have this secondary alkyl bromide, and then let's put a deuterium in this molecule. So deuterium is just an isotope of hydrogen. It has twice the weight of the hydrogen, but otherwise chemically very similar. And then I say this is apparently kind of a silly SN2 reaction because the nucleophile that we're going to use is going to be identical to the leaving group. All right? So the first thing for you to try to do is to draw the SN2 reaction. And you know, maybe this is a silly SN2 reaction, but go ahead, push the arrows, draw the product, and respect the stereoelectronic requirement for the SN2 reaction that you're now very familiar with from your study of that chemistry. All right, so the stereoelectronic requirement for the SN2 reaction is that the nucleophile has to come in exactly opposite where the leaving group is leaving. So in this particular case, here comes the nucleophile, exactly 180 degrees away from where the leaving group is, and then the leaving group simultaneously departs. So if you didn't get a chance to draw the product, you can go ahead and do that now. The key to this is that the bromine that makes the new bond to carbon comes in from the side directly opposite where the leaving group is departing. So you see this carbon-bromine bond was pointing in this direction, but now that carbon-bromine bond is pointing in the other direction. So what is the fate of the methyl, the hydrogen, and the deuteriums? Well, fill those in if you can on this structure. Remember, this carbon has to be tetrahedral. So we're going to have a methyl there. And then this hydrogen will come over to here, and the deuterium is going to be there. Okay? So just for the sake of comparison, let's call this compound A, and let's call that compound B. And the question I want to ask you now is, what's the relationship between compound A and compound B? Are these two, for example, the same? In other words, if you built a molecular model of A, just exactly like I've drawn it here, and you built a molecular model of B, exactly as it's drawn over here, and you tried to take those two molecular models and turn them in some way and overlay them, would the atoms match atom for atom? So another way of asking, are they the same, is to ask, are they superimposable? Sometimes people say this word, and I think maybe this is even technically more correct. Superposable. Those two mean the same thing. I will tend to say it this way, but you'll hear people say it that way. Are they superimposable atom for atom? So try to make some conclusion about that. The problem with trying to compare these on a flat surface is that if I try to scoot B over here and put it on top of A, this bromine is pointing in the wrong direction to even try to match things up. So here's what I want you to do to help answer this question about whether these are the same. So let's redraw B. So this little symbol means just is exactly the same as, is equivalent to. And what I want you to do is I want you to imagine some axis like this, and then just take this drawing and rotate it around by 180 degrees. The picture you're going to generate is the same molecule B. It's just turned over by 180 degrees. So when you do that, I'll get you started. This bromine is going to be pointing in the other direction. The virtue of that picture is that it's going to be easier to compare to this one. So can you redraw B following a 180 degree rotation around a vertical axis like that? Well, now the bromine goes this way. This methyl is over on this side, like this. And then the somewhat tricky part of this is when you turn this over by 180 degrees, this hydrogen, which starts out toward my eye, now goes back into the board. So it's back here. And then this deuterium is here. So that is still compound B, just redrawn. So does this picture help you compare to A and answer the question, are they the same? Well, at this point, we could just scooch B over here. The bromine, the carbon, and the methyl would match. But unfortunately, the D, well, I guess not unfortunately or fortunately, that's not really, I guess, an issue here. The D is on the wedge here. It would be lying on top of the hydrogen, and the D there would be lying on top of that hydrogen. So no, they are not superimposable. So the conclusion here is no, not the same. And now we want to know really, what are they? If they're not the same, they seem to be very similar, right? I mean, this carbon has a bromine, a methyl, a hydrogen, and a D, and this has all the same 4 groups attached to it. So what exactly is their relationship if they're not the same? And what I'd like to do is just to come over here to this corner of this board here. Let me just redraw A. So here it is. And then I want you to imagine just putting a mirror. So this is a mirror. And you're just putting a mirror right in front of A. And what is the mirror image of A? So if we draw the mirror image on the other side of the mirror, if you will, when you draw a mirror image, what you're doing is you're reflecting each point of this molecule through a plane onto the other side. So you just take a point, say where the bromine is, you go some distance to the plane, and then you go that same distance and you draw the bromine again. So can you draw the rest of this, its mirror image, on this side of the mirror? Well, if you do that, the carbon is here, so you go some distance to the mirror and then you go over that same distance. With the methyl's mirror image would be over here. The hydrogen's mirror image would be leaning this way, but still on the wedge. And the D would now be leaning this way, but still on the dash. Okay? So let me just demarcate these things here a little bit. And look at this. Let's compare this structure to this picture up here. That's just B, isn't it? So what are A and B? They're not the same. Okay, so no, they're not the same. And they are mirror images. So what we have here are non-superimposable mirror images. A and B are non-superimposable mirror images. And there's a special term for that relationship between A and B. So we say they are enantiomers. So here we have to consider a little bit, of kind of semantics here. Enantiomers is a relationship. So A and B are enantiomers of each other, kind of like I'm the brother of somebody, okay? And somebody is my sister. So that's a relationship. There's a property that goes along with having an enantiomer. So that property is said to be chirality. So chirality, kairos is the Greek word for hand. And so if you have some object that is not identical with its mirror image, you say that that object is chiral. So it would be proper then to say that B is chiral, and so is A. So see, that's not a relationship, that's an independent property of A and B. Each of them is chiral. Because they're chiral, they have an enantiomer, and so A and B in this example are enantiomers of each other. Okay? A and B being enantiomers, that's a class of stereoisomerism, and the module that we're going to start, that you're watching this video as a preview of, has to do with stereoisomerism, and in particular this concept of chirality and the presence of enantiomers. Here's a similar problem. Hopefully you can work through it. So once I get this up on the light board here, please pause the video, and I'd like you to work through this in a manner exactly analogous to the previous exercise. Again, I have this seemingly silly, and maybe this is even sillier than the previous one, but anyway, we'll see what happens. Alkyl halide nucleophile. And so what I want you to do here is I want you to carry out the SN2 reaction, again, respecting the backside displacement of the leaving group by the nucleophile. Let's call this compound, well, we used the letters A and B before, so let's call this C. The product that you're going to generate we'll call D. So do the same thing that we did before. So you're going to carry out the backside displacement. You're going to draw D, showing clearly how that backside displacement has led to the new structure. And then you're going to compare D to C and ask that question, what is the relationship between these two? Are they the same? Are they something other than the same? Okay, so pause the video and give that a whirl. All right, so it's going to be pretty much exactly like we did before. Here comes the nucleophile, right from the backside of where the leaving group is leaving. And then when I get over to this side, that's going to lead to the carbon-bromine bond pointing from here to here in that direction, whereas this carbon-bromine bond pointed in that direction. And then this methyl group will have ended up on this side. This hydrogen is this hydrogen here. And this hydrogen that's in the back is this hydrogen right there. Okay? So maybe you got a picture that looked like that. The next question was, what is the relationship between C and D? And again, the problem here is that if I just try to slide this over to make a comparison directly, the bromine is pointing in the wrong direction, and so that makes it hard to compare. So I'm just going to redraw D again by rotating 180 degrees around a vertical axis. And when I do that, I get another picture of D. Have you drawn it? Well, the bromine goes this way. This methyl ends up here. And if this is not working out for you, you really should verify it with your molecular model set. So build the models and compare the models to what you're actually drawing. So here's an interesting thing, right? This hydrogen that's in the back, when you rotate it around, if you're keeping track, this hydrogen ends up here, and this hydrogen ends up there. But the difference between this problem and the last problem is that, well, hydrogen is hydrogen. And, these two hydrogens are the same. So now compare this. What is the relationship between D and C? If I take this picture and I just slide it over to there, what do you think? Well, from this picture of D, it's pretty clear that C and D are not any different from each other. They are exactly the same. They are superimposable atom for atom. So, are C and D enantiomers? No, they are not. Enantiomers are non-identical mirror image molecules. Is C chiral? Well, let's draw the mirror image of C and see whether it's any different from C itself. So let's come over here and just redraw C. Here's C. And maybe you recognize that the mirror image is already lurking around on this light board somewhere, but let's just go ahead and work through it like we did the last time. There's C. Here's the mirror plane. I'll just make it a little bit more stylized. I'll just draw it as a line here rather than trying to draw the whole plane thing. So can you draw the mirror image of C over here? Okay, can you do that? Take the bromine, go some distance, go the same distance on the other side of the plane. Carbon to the plane, same distance to here. Methyl, some distance to here. This hydrogen reflects over to here. and this hydrogen reflects over to here. Okay? Everything has a mirror image. Well, there's one category of things that do not have a mirror image, and maybe we'll talk about it in class tomorrow. Can you think of something that does not see itself in the mirror? Okay? But anyway, everything has a mirror image, but not all mirror images are different from the original. So yes, this is the mirror image of C. You may notice that this is exactly the same as this picture. So the mirror image of C is actually D, and we said that D and C are the same. So in this particular case, C's mirror image is identical with the original. So a molecule whose mirror image is identical with the original, is it chiral? Remember that chiral comes from the word for hand. Is the mirror image superimposable? Yes, it is in this case. So is C chiral? No, it's not chiral. And D, well, it's the same as C. This isn't chiral either. Maybe I don't even need to write that, but okay? So not all molecules are chiral. The way to test for chirality is draw the mirror image like we did here, and then ask the question, is the mirror image different or the same from the original? If it's different, then the molecules are chiral and they are enantiomers of each other, the two mirror images that you've drawn. But if they're the same, then the original molecule is not chiral. Let's just look at the two molecules that we've examined so far. One of them looked like this. It had an H and it had a D there. And we showed that this was non-identical with its mirror image, so this one was chiral. And then the other one we looked at had also a bromine and also a methyl on the carbon, but then it had just an H and a second H. And we said that this was not chiral. Another way of saying not chiral is to say that a molecule is achiral. You do have to be a little bit careful about the timing of that word, because if you put too much time between the A and the chiral part, there's room for confusion, right? This is a chiral molecule would be wrong, but if you said this is achiral, then you would be right. You see what I mean? So just, if you use this term, just be sure you say it correctly. Look at these structures. This one turned out to be chiral. This was not chiral. What's different about the pink one versus the blue one in general terms? Could we generalize what element does this chiral molecule have that the blue one does not? This molecule is a molecule that has a tetrahedral carbon. So tetrahedral, that means sp3 hybridized. And it has 4 different things attached to that tetrahedral carbon. So 4 different groups at, let's just say, the carbon with a little star. Okay? So if we're just going to generalize that, we might just draw something like this: R1, R2, R3, and R4, where none of these 4 groups is the same. So R1 is not equal to R2, is not equal to R3, is not equal to R4. Whereas this one doesn't meet that requirement, right? So we call this type of carbon, sometimes it's referred to as a chiral center. It's a genesis of chirality, a genesis of stereochemistry. So another term might be stereogenic center. So as we talk more about stereochemistry, certainly be on the lookout for carbons that are tetrahedral sp3 hybridized carbons, and that all 4 things on the carbon are distinct from one another in this kind of general sense. That's often a center of stereochemistry. All right, here's a question I want to ask you. We saw the last time that a carbon with 4 different things attached to it, sp3 hybridized, was a potential source of having a chiral molecule. So what I want to ask now is the following. is a carbon of this type, tetrahedral carbon with 4 distinct non-identical groups attached, is this stereocenter, is this kind of carbon necessary in order to have a chiral molecule? So if you're a philosophy major or a student of logic or whatever, you know that a question like this, if you can find even one case of a molecule in which the molecule is chiral, but it doesn't have one of those, then you can say that that type of element is not necessary in order to have a chiral molecule. Okay, so you may be able to guess what the answer to this question is based on this fairly long-winded preamble, but let me give you a molecule. It's kind of an unusual molecule, perhaps, by the standards of this class so far. There are 2 carbon-carbon double bonds emanating from the central carbon right there. And then at this carbon, there's a hydrogen and there's a methyl. And then you may want to think about why this is the geometry of this molecule. We won't concern ourselves too much with that. We'll just take that as a given. But this hydrogen is actually back behind the plane, and this methyl is in front of the plane. All right, so is this carbon right here, is this a carbon that's sp3 hybridized with 4 different things attached? No, it isn't, right? Because 3 of those things are hydrogen. How about this carbon? Is this carbon sp3 hybridized? No, it isn't. What's its hybridization? sp2. How about this carbon? That's certainly not sp3 hybridized. What is it hybridized? That's kind of an interesting case. That's sp hybridized, right? So this is sp2, this is sp, and this one is also sp2. So does this molecule have any sp3 hybridized carbons of this type? No, it does not. Okay? So your job then is to look at this molecule. Here's your mirror. So here's the mirror. This molecule wakes up, goes to the bathroom and looks at itself in the mirror. And what does it see? Can you make the picture of the mirror image of this molecule? Well, when you draw the mirror image, you just reflect through this point, okay? Or through this plane. So let's go from this carbon to the plane and a distance this way. Let's go from this carbon through the plane and the same distance that way. This carbon reflects over to here. Double bond there, double bond there. This carbon is this carbon in reflection. This methyl group will be here. This hydrogen will be there. Can you draw in the rest? This methyl is going to be here. And this hydrogen is going to be there. Okay? So let's see. The previous problems, we had compounds A, B, C, and D. So I guess we're up to E. Let's call this E. And then let's call this F. And so the game now is, what is the relationship between E and F? We've drawn them as mirror images, right? They're either identical to each other or they're not. So what do you think? Well, you know, you might just try to slide this over. These 3 carbons would certainly match those 3. But, you know, this methyl's out of the plane and that hydrogen's in the plane. So it doesn't look like ideal for comparison. So let's do, you know, something similar to what we've done already. Let's redraw F. So I just want to generate another picture of F. But let's rotate it by 180 degrees around the vertical axis. So can you just redraw F rotated by 180 degrees? Here is the 3 carbon unit here in the middle. This carbon now is over here. This carbon is over here. When I turn that molecule over, this methyl group goes to the back. This hydrogen comes to the front. So trigonal planar geometry here, but we're viewing the trigonal plane on edge. This methyl here ends up there. So this methyl goes there, and this hydrogen would go there. So that's a little bit easier to compare, perhaps, right? I could just slide this over. This hydrogen and this methyl, they're going to match. All of this is going to match But where's the rub, as Shakespeare might write? Well, look at this. This hydrogen is going to end up where this methyl is. This methyl is going to end up where that hydrogen is. So are E and F the same? No, they're not. Okay, they're not superimposable. They are mirror images. We've drawn them as mirror images. So non-superimposable mirror images, their relationship is, what is E to F? These are enantiomers of each other. So E and F are enants of each other. Is E chiral? Yes, it is. Is F chiral? Yes, it is. So the answer to our original question, is this type of sp3 hybridized carbon with four different groups attached to it, is that necessary in order to have a chiral molecule? No, it is not. It is very common, no doubt, it is very common that chiral molecules do have carbons of that sort. I had to kind of, drag out a fairly unusual structure, at least by the standards of this class, in order to find an example where I do have a chiral molecule without one of these. So I would say, yes, the vast majority of examples of chiral molecules that you will see in this course do, in fact, have one or more of these types of carbons, but not all. And this is a good example. The other thing I would really like you to remember from this practice problem is that if I ask you, is a certain molecule chiral? The surefire way to answer that question is to put up the mirror plane, draw the mirror image, and then make a decision as to whether the mirror image is identical to the original or not.